In this video, we're going to finish up our discussion of techniques for computing limits. This is the second part, and we're going to talk about infinite limits and limits at infinity. So let's go ahead and get started here. Our objectives will be to conceptually discuss end behavior and horizontal asymptotes, to evaluate limits at infinity, to find horizontal and vertical asymptotes of functions using information about limits, to determine end behavior of transcendental functions and sketch their graphs, to find slant asymptotes and sketch the graphs of rational functions, and to solve applications involving limits used to find steady states. Steady states are going to be things where the limit goes to infinity. Just a quick note here, we never, ever, ever direct sub infinity or negative infinity. They're ideas, not numbers. We can't direct substitute them. We can just look at the graphs and know what the limits do with the end behavior. So again, let's come back to 1 over x and 1 over x squared. This time we're going to talk about 1 over x squared, and the graph looks like this with a vertical asymptote here at x equals 0, horizontal asymptote here at y equals 0. So the limit as x approaches 0 from the right of 1 over x squared is going to be positive infinity. Really, we could write out the limit does not exist because it increases without bound, but we don't want to write all those words, and we write an answer of infinity, even though infinity is not a number L. It's not a finite number L. We write this symbol to replace all those words that the limit does not exist because it increases without bound. As the limit as x approaches infinity from the left of 1 over x squared, it also goes to positive infinity. So let's look now as limit as x goes to positive infinity over here, the right hand end behavior over here of 1 over x squared is going to go to 0, and the limit as x goes to negative infinity, the left-hand end behavior over here of 1 over x squared is also going to go to 0. At x equals 1, 1 over 1 squared is equal to 1. At x equals 1/2, 1 over 1/2 squared, so 1 over 1/4 is equal to 4. And at x equals 1,000th, equals 1 over 1,000th squared is 1 times 10 to the 6th is 1, 1, 2, 3, 5, 6 is 1 million. At x equals 10, y equals 1 over 10 squared is 1 over 100, or 1,000th. At x equals a million, y equals 1 over 1 million squared is 1 times 10 to the negative 12th is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? If you're uncertain about a limit to infinity, make a table like this, where you can say, as I get closer and closer to 0, I'm getting closer and closer to infinity. That was these first few here, to show that there's a vertical asymptote going to infinity here. These, as x is getting bigger, y is getting closer and closer to 0. So let's go ahead and look now at 1 over x instead. It looks like this. And I have limit x approaches 0 from the left of 1 over x is going to negative infinity. Limit as x approaches 0 from the right of 1 over x is going to positive infinity. So notice that that's different signs as I change sides of the asymptote. Limit as x goes to infinity, 1 over x is going to 0. And limit as x approaches negative infinity of 1 over x is also going to 0. We could look at some numbers here to make a table. If we wanted to figure out what's going on here, we could look at, say, x equals -1. Y is going to be -1. X equals -1,000. Y equals -1,000. X equals -1,000,000. Y equals -1,000,000th. Like that. So infinite limits will be vertical asymptotes. So the notation, limit as x approaches a of f of x equals infinity means that the values of f of x can be made arbitrarily large as we please, conceptually trending larger and larger by taking x sufficiently close to x equals a, but not equal to x equals a. So another way to say this, the limit does not exist because it increases without bound. Okay, the line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following is true. Limit as x approaches a of f of x equals plus or minus infinity, or limit as x approaches a from the left of f of x equals plus or minus infinity, or limit as x approaches a from the right of f of x equals plus or minus infinity. So any of these things will cause a vertical asymptote in the graph. It's okay for us probably in this class to say the limit of f of x as x approaches a is infinity. We'll understand that that means the same thing as this thing here. All right, let's go ahead and take a look here. As x approaches 3 from the left, this is smaller than 3, and I have a positive over a negative is going to go to a negative infinity here. As I get x approaching 3 from the right, this is a positive down here number, and a positive over a positive is going to be a positive infinity. This -4 isn't going to change this infinity that's so large. So it's insignificant, and I don't really pay any attention to it. If we want to sketch graph of f of x is equal to 2 over x minus 3 minus 4. We're going to have a horizontal asymptote at -4. We're going to have a vertical asymptote at 3. To the right, we're going to positive infinity. And let's see, where is that going to happen? 2 over x minus 3 equals 4. 2 equals 4x minus 12. 4x equals 14. X equals 7 halves is 3.5. So right there, it's going to cross over like so. And then we're going to have a y-intercept here of -2/3, -4 2/3 is right there. It's going to come at it from this side. And I don't think that I'm ever going to cross there. All right, so we'll never cross that horizontal asymptote. In this case, some cases I might, but our parent function was y equals 1 over x, and I shifted that 3 to the right and 4 down, and then stretched it by a factor of 2. So we could alternatively say, locate the vertical asymptote of this function, and how do we know that it's a vertical asymptote? So we would know it's a vertical asymptote because as I take either of these one-sided limits here, it's going to positive or negative infinity. That automatically makes it a vertical asymptote. All right, let's talk about limits at infinity. Horizontal asymptotes y equals a constant number is what we're going for here. So let f be a function defined on the open interval of a to infinity. Then the limit as x goes to infinity of f of x equals L means that the values of f of x can be made close to y equals L by making x sufficiently large. We would say something like the limit of f of x as x approaches plus or minus infinity equals L. If we're approaching positive infinity, we're going to talk about right end behavior of the graph. If we are talking about negative infinity, we're talking about left end behavior of the graph. So the line y equals L is called a horizontal asymptote of y equals f of x if either limit as x goes to infinity of f of x equals L or limit as x goes to negative infinity of f of x equals L. There are some special cases in math where we can have two different horizontal asymptotes, but I do not believe that you are going to encounter many, if any, of those situations here in this class. I'll see if we have any of those examples come up, but we're going to have a finite number L not plus or minus infinity for our answer. If we go to infinity and get plus or minus infinity for our answer, it's not a horizontal asymptote. So as I divide 2 by a really large number, this is getting close to 0 minus 4 is -4. As I divide 2 by a really big negative number, I'm getting close to 0 minus 4 as well as a -4. And so I would look at that graph that I already made up here and show you that there's a horizontal asymptote at y equals a -4. I had a vertical asymptote at x equals 3. We've already drawn that out. Don't need to do that again. Our alternative problem statement might say locate the horizontal asymptote of f of x. And how do you know it's a horizontal asymptote of y equals -4? It didn't matter whether we took the limit as x went to positive or negative infinity. We got f of x was approaching -4. Let's look at this one here. Limit as x goes to -infinity of 2 plus 10 over x squared. So let's draw this graph here. This is based off of 1 over x squared, but it's going to be shifted up 2. So we have a horizontal asymptote up here at y equals 2. We still have a vertical asymptote here at x equals 0. And we've multiplied by 10. So things are going to be growing a lot faster here. And be something like that. And our limit as we go to -infinity over here is going to approach 2 plus 0 is 2. Let's talk about infinite limits. Limits at infinity that are going to be n behaviors of polynomials. So polynomials of an even degree are going to resemble the n behavior of y equals x squared. Limit as x goes to infinity of x squared is equal to positive infinity. Limit as x goes to -infinity of x squared is equal to infinity. If we have y equals a negative x squared, limit as x goes to infinity of negative x squared is equal to a -infinity, and limit as x goes to a -infinity of negative x squared is also a -infinity. So this is the characteristics of even polynomials with positive leading coefficients. This is characteristic of even polynomials with negative leading coefficients. All right. Let's look at an odd degree polynomial. Something like y equals x cubed. Limit as x goes to positive infinity of x cubed. That right-hand n behavior is going to positive infinity. Limit as x goes to -infinity of x cubed is approaching a -infinity down here on the left-hand side. And that will be characteristic of odd polynomials with positive leading coefficients. have y equals a negative x cubed. Looks like that. Limit as x approaches infinity of a negative x cubed is a negative infinity. Limit as x approaches negative infinity of a negative x cubed is equal to a positive infinity. That will be characteristic of odd polynomials with negative leading coefficients. So those are basic examples. If we forget the definition below, this definition is hard to look at. So we'll just try to remember those basic graphs to help us understand this. So this is the degree of the polynomial here is equal to n, and the leading coefficient is a sub n. So our limit as x goes to plus or minus infinity of x to the n when n is even, assuming that a sub n is greater than 0, will be a positive infinity. The limit as x approaches infinity of x sub n equals infinity, and the limit of x sub n as x approaches negative infinity equals negative infinity when n is odd. Again, assuming a sub n is positive here. Limit as x goes to plus or minus infinity of 1 over x sub n equals limit as x goes to plus or minus infinity of x to the negative n is equal to 0 for n being even or odd. They'll have a horizontal asymptote at y equals 0. Limit as x goes to plus or minus infinity of p of x is equal to limit as x goes to plus or minus infinity of a sub n x to the n will be plus or minus infinity depending on the degree of the polynomial, even or odd, and the sign of the leading coefficient a sub n. Remember the sign of a sub n changes the end behavior, or say affects the end behavior. Part of the calculation, you can't ignore it. So for example here, if we had limit as x goes to negative infinity of a negative 4x to the 7th plus 9x minus 1, this is going to be a negative infinity because this is an odd number of negatives here, times a negative number is a positive infinity. It's going to go up and to the right. Because a sub n is negative 4, we're thinking, think y equals a negative x cubed in this case because it's negative and odd, and that was falling to the right and rising to the left. So as I go to negative infinity, it's rising in the positive infinity direction. All right, let's look at end behavior of exponential and logarithmic functions. Let's consider f of x equals e to the x and g of x equals ln of x. We know e to the x looks like this. We know ln of x is going to look like this. This crosses at 1, 0, and this is at 0, 1, something like that. So limit as x goes to negative infinity of e to the x is 0. Limit as x goes to positive infinity of e to the x, the right hand end behavior here is infinity. Limit as x goes to 0 of e to the x is equal to e to the 0 is 1. Limit as I come from the right of 0 of ln of x is going to go to a negative infinity. Limit of ln of x as x goes towards infinity is going to be positive infinity. It goes forever up and to the right. Ln of x does not go to negative infinity. This limit does not exist because I can only get to 0 from the right. So for x less than or equal to 0, ln of x is undefined. Right? Also, y equals e to the negative x has interesting behavior. That is a exponential function that falls to the right like that. It also goes to the point 0, 1, and it has a horizontal asymptote over here on the right of y equals to 0. So limit of e to the negative x as x goes to infinity is going to be 0. Limit of e to the negative x as x goes to negative x is going to be positive infinity. And this is still going to be e to the negative 0 as e to the 0 is 1. So we have a reflection over the y-axis. That's what happened here. If you remember your transformations from pre-calculus, that negative sign in front of x made a reflection over the x-axis. Let's talk about the end behavior of a rational function. End behavior and asymptotes of rational functions. Suppose f of x is equal to p of x over q of x is a rational function where p of x is equal to a sub m x to the m plus a to the m a sub m minus 1 x to the m minus 1 plus dot 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 plus a2 x2 plus a1 x1 plus a0, and q of x is equal to b sub n x to the n plus b sub n minus 1 x to the n plus dot 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 plus b2 x2 x squared plus b1 x plus b0, with am not equal to 0 and bn not equal to 0, where the degree of p of x is equal to m. Degree of q of x, so we're going to call that n, and a sub m is the leading coefficient of p of x. A sub b sub n is the leading coefficient of q of x. All right. If the degree of the numerator is less than the degree of the denominator, if m is less than n, then the limit as x goes to plus or minus infinity of f of x has to equal 0, and y equals 0 is a horizontal asymptote of f. You learned that rule in pre-calculus. If the degree of the top was less than the degree of the bottom, you had a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then there is a horizontal asymptote at the ratio of the leading coefficients here. So limit as x goes to plus or minus infinity of f of x is equal to a sub m divided by b sub n, and y equals a sub m divided by b sub n is a horizontal asymptote. Don't forget to reduce that fraction. And then if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. There's going to be an oblique or a slant asymptote. The limit is going to go off to positive or negative infinity. And we'll have to use long division to figure out the equation of the line that it approaches. So will be a slant or oblique asymptote. Use long division to find it. All right. Let's evaluate the following limits analytically. Limit as x goes to infinity of x plus 1 over x squared minus 2x. We're going to multiply top and bottom by the reciprocal of the biggest power in the denominator. And that's going to give me limit as x goes to infinity of 1 over x plus 1 over x squared over 1 minus 2 over x. Anywhere that I see an x in the denominator or a negative power of x, that's going to go to 0. So this is 0 over 1 is 0. All right. Let's evaluate it with the with the rule from up here. The degree at the top was less than the degree at the bottom, so we have a horizontal asymptote of y equals 0. Same thing. Degree of the denominator is greater than the degree of the numerator, and that means horizontal asymptote at y equals 0. All right, let's find the limit of x cubed plus 2x plus 1 over x cubed minus 3. We can use our theorem to tell us that we have a degree of 3 in the numerator and a degree 3 in the denominator. So we're going to look at the ratio of the leading coefficients. 1 over 1 is 1. Let's do that with our new algebra technique. Limit as x goes to negative infinity of x cubed plus 2x plus 1 over x cubed minus 3 over x cubed. It's going to be the limit as x goes to negative infinity of 1 plus 2 over x squared plus 1 over x cubed for 1 minus 3 over x cubed. It's going to go to 1 plus 0 over 1 minus 0 is going to be equal to 1 over 1 is 1. Let's determine the end behavior of f of x is equal to 2x squared plus 6x plus 2 over x plus 1. So this is degree 2. This is degree 1. So we have no HA. We're going to have an oblique asymptote. We're going to need to use long division here to interpret what's going on. Let's just try to find the limit to see if it's going to plus or minus infinity. Then I'll go back and I'll show you how to find what the actual equation is. So limit as x goes to infinity of 2x squared plus 6x minus 2 over x plus 1. We're going to multiply by 1 over x, and 1 over x is going to be limit as x goes to infinity of 2x plus 6 minus 2 over x over 1 plus 1 over x is going to approach a positive infinity over a positive number is going to be positive infinity. Limit as x goes to negative infinity. This would be my left end behavior. This would be my right end behavior. Again, 2x squared plus 6x minus 2 over x plus 1. Going to multiply by 1 over x. And this is going to be limit as x goes to a negative infinity of 2x plus 6, 2 over minus 2 over x, 1 plus 1 over x. So this is going to become a negative infinity up here over a positive 1. It's going to go to a negative infinity here. Now, let's ask the question, is there a slant or oblique asymptote? All right. Let's look again. F of x is equal to 2x squared plus 6x minus 2 over x plus 1. And we're going to set up polynomial long division. X plus 1 into 2x squared plus 6x minus 2. It's going to be 2x squared, and 2x, subtract. 4x, bring down the negative 2. 4x divided by x is a positive 4. It's 4x, and then 4 times 1 is 4. Change my signs and add. You have minus 6 over x plus 1 is our remainder. We ignore that part because that part's going to 0, and we have an oblique asymptote or a slant asymptote, whatever your book calls it, of y equals 2x plus 4. Specifically, we get a slant asymptote, the equation of a line, if the degree of the top is exactly 1 degree higher than the degree of the bottom. It's usually what we're looking for. So there it is. And let's look at an advanced example of a limit going to infinity here. So we would want to think about, this is really the square root of x to the 6th is x to the 3rd. So we're going to multiply by 1 over x to the 3rd, and then on the right-hand side over there, this is the same thing as 1 over the square root of x to the 6th. Because I'm on the right-hand side, I have a positive number here. It's not something that I need to worry about. X is a positive number, so I'm going to get the same thing. Remember that the square root of x squared is equal to the absolute value of x. So I need to think about when I have an even number on the inside that comes out as an odd number on the outside, like this would, if I pulled it out, that it really is x if x is greater than or equal to 0, and it is a negative x when x is less than 0, because it's equal to the absolute value of x. So a couple of different ways we can deal with that, but I'm going to just put this on the inside like that, and so come here and make this 10 minus 3 over x plus 8 over x cubed, and this is square root of 25 plus 1 over x squared plus 2 over x to the 6th, and that is going to give me 10 over the square root of 25. This is minus 0 plus 0. This is plus 0 plus 0 is 10 over root 25 is 10 over 5 is 2. All right. If you wanted to do it the other way with the pulling the x to the 6th out, I'll show you that. We're going to have the absolute value of x to the 3rd. square root of 25 plus 1 over x squared plus 2 over x to the sixth. And then this is 10x to the third minus 3x squared plus 8. And I'm going to identify that on the right-hand side over here, the absolute value of x cubed is x cubed. This is limit as x goes to infinity of x cubed, square root of 25 plus 1 over x squared plus 2 over x to the sixth, 10x cubed minus 3x squared plus 8. Divide all of these things up here by this x cubed, and I get 10 minus 3 over x plus 8 over x cubed, root 25 plus 1 over x squared plus 2 over x to the sixth. And I still get 10 over root 25. This 10 over 5 is 2. Either way, I get the same answer. So how many horizontal asymptotes can a graph of y equals f of x have? Sketch an example. At most 2. Usually 1 or none. So limit as x approaches 2 of f of x is equal to negative infinity on both sides here. Limit as x goes to negative infinity is 0. I don't know if that's from the top or the bottom. Over here, I'm getting close to 0. So I get close to 0 from the left. I'm going to negative infinity here. As I get close to 0 from the right, I'm going to positive infinity here. Right-hand behavior is going off to infinity somehow, some way. So let's let this graph come down here, and then maybe cross like so. And then there's nothing saying that this can't cross in there, and it does, like that. And it might, it's going to go off maybe like this. Might be a good way to make it go off towards a oblique or slant asymptote of some kind. Like that, we just don't know. So we have options here for question 1. We can have no horizontal asymptote for a graph like y equals x squared. We can have one horizontal asymptote. For example, y equals e to the x. That we could, and I'm not going to tell you what this function is because it's not in the class, but I'm just telling you such a function exists where I can make the function stay between 2 lines like that, but 3 or more horizontal asymptotes is impossible. Okay. I can get might be a better function to draw for this, but I can get a rational function sometimes that will look kind of like that one, but not be the one that I was drawing, where it will, especially if it has a square root in it, where it will come up and it will approach a horizontal asymptote up here. maybe coming and crossing like that. And then on this side, maybe it crosses and comes like that, where this is, say, y equals 1, and this is y equals -1. That can definitely happen. So let's see if we see any of those. Did I do that? Yeah. So first thing we want to do is put any points on the graph that we have, and then determine vertical asymptotes, and then determine end behavior is the next thing. So this is a decent representation. There's nothing saying that I'm going to a slant asymptote here. I could just go off to infinity because the power is increasing like that. I do have this horizontal asymptote over here at y equals 0, but it's only on the left-hand side. All right, let's evaluate. Following limits. Limit as x goes to infinity of -2x to the fourth minus 6x squared plus 3x minus 9 is going to be right-hand end behavior of a negative even-powered function. So I'm thinking this type of a graph, right-hand end behavior, that's going to go to -infinity. Remember, you can't do direct substitution. You can't remember the end behavior. What the end behavior is, graph the parent function that this is negative leading coefficient even power function. So that's what I did there. So that was my first example. Let's look at my second example here of limit as x approaches 1 from the left of x plus 1 over x minus 1. And I want to see what's going to happen here. If I try direct substitution, I get 2 over 0, which is undefined. There's an asymptote there, so now I need to think about, well, I'm coming from the left-hand side, and what does this function look like? Let's go ahead and stick a number a little bit less than 1 in, and I'm going to get a positive over a negative. Is going to be a negative when I come from the left. Down here, this is going to go through -1 and cross at -1. Like that. And get close to 1 down here. And this one, this piece is going to be a reflection up here. A reflection over that point. And as I come from the left, I'm going to a -infinity is what's happening. What about if we would take the limit as x approaches 1 from the right of that same graph? That's going to go to positive infinity, right? All right, so that's it for this video. We'll come back next time and we will start introducing the derivative, which builds on the concepts of limits and continuity. You'll see why we needed to talk about those before we talk about derivatives, and derivatives make a really, really big piece of this class. Most of this class is talking about derivatives and applications of derivatives. Very little of this class talks about antiderivatives and applications of antiderivatives. I'd say 3/4 of this class has to do with limits, continuity, and derivatives. So, all right, see you back here next time for our introduction to derivatives.